Go to page 13 of your magnetic field notes. The whole voltage part, I'll leave it for last. Okay, so go to page 13 first of your magnetic field notes. Okay, now, as you have learned previously, I told you that if you have a charged particle and it enters a magnetic field perpendicular to it, your charged particle will actually move in the arc of a circle. Okay, right? It will always move in the arc of a circle if the only force acting on it is your magnetic force. Okay, now there are cases where when you have a charged particle that is moving inside a magnetic field, you apply an electric field at the same place where you have a magnetic field so that your charged particle moves straight. Okay, so the reason why we want to do that is so that we can select particles of a specific velocity. Like just now, if I told you that you have a charged particle that enters a magnetic field, and that charged particle, because it experiences a magnetic force, the magnetic force causes your charged particle to move in a circle. But what if you put an electric field at the same place where you have your magnetic field, such that you have a electric force opposite to your magnetic force? Okay, if you go and put a electric field in such a way that you have an electric force that is opposite to your magnetic force, it will come to a point where your charged particle can actually move in a straight line. Okay, the reason why you want your charged particle to move in a straight line is so that you're able to select particles of a certain velocity. In some practical applications, you have a source of charged particles. Okay, you have a source of charged particles. Okay, you have particles that are being emitted with a range of speeds. Maybe this one is 10 meters per second, this one is 20 meters per second, this one is 30 meters per second. So for your application, you want to have a velocity, a certain velocity only. Maybe say you want 20 meters per second. The rest of it you do not want. So how do you go about doing it is that you need to take this group of charged particles, you pass it through a combined electric and magnetic field. So you need to do some adjustment to the field such that the charged particle that moves straight through is moving with the speed that you want. Okay, that's what this thing here is what you call a velocity selector. Okay, it has a combined electric and magnetic field that allows you to select charged particles with a certain velocity only. Okay, so how it works is basically something like this. As I mentioned, you have two fields, your electric field and magnetic field, that are placed perpendicular to each other. Okay, the goal is to have only a particle of a certain velocity move straight. That is the particle that you want. Okay, so if you're considering the particle right now that is moving straight through with the velocity that you want, you consider the forces acting on the charged particle. If say this is an electron moving straight with velocity v towards the right, your conventional current would be opposite direction. You use your Fleming's left hand rule, you notice that your magnetic force is acting downwards. Okay, now then after that you apply electric field such that your electric force is opposite to your magnetic force. This one will be your Fe. When your charged particle is moving straight through, your Fb is actually equals to Fe. This is when your charged particle is moving straight. Okay, the ones that you've always done so far was Fb equals to Fc. That one was when you have a magnetic field only and your charged particle was moving through it. That one is only for this case where there is only magnetic field. Okay, when you say Fb equals to Fc, this one is normally a case where you have B field and E field, like in this case here. In this case here, when you have the magnetic field and electric field, where you say magnetic force is equals to electric force, is talking about case of your charged particle moving straight, not in a circle. The one that's moving in a circle is for this case, where you have only magnetic field, your charged particle moves in a circle due to your magnetic force. But for this case here, where you combine electric and magnetic field, you have electric force and magnetic force. If you say they are equal, it causes your charged particle to move in a straight line. Okay, so if you say FB is equals to FE, the magnetic force acting on the charged particle is BQV, the electric force acting on the charged particle is QE. Eventually, you'll be able to simplify it to this. V is equals to E over V. Okay, your FE came from this one. Electric field strength is actually electric force over charge, force per unit charge. That's how you got this. Okay, so put this inside here. FE is equals to QE. You get this. All right. Then you simplify, you get V equals to E over B. This is actually the velocity of charged particle that is moving straight. Okay, so if you want to change the velocity of the particles that were moving straight, you want to select different velocities, all you just need to do is that you just need to change the magnetic and electric field strength. Okay, that's how you are able to select the velocity of the charged particles. Okay, so this came from this relation. Okay, now just now as I mentioned to you, you have a case where sometimes you have a source of charged particles. The charged particles are emitted with a range of speeds, right? So I just now told you that it could be that you have a source of charged particles and the charged particles were moving with a range of speeds. And when you pass them through a velocity selector or combined electric and magnetic field, you actually just only want to select one particular speed of the charged particles, right? What about the other particles that weren't at the speed that you select? Let's just say the speed that you select here was 200 meters per second. But then the rest of the charged particles were not at that particular speed. Maybe this one was moving at 150 meters per second. This one was moving at 280 meters per second. One of this one is lower than 200 meters per second. This one is larger than 200 meters per second. So what happens to these two particles with two different speeds? Okay, you will need to determine whether that particle will deflect upwards or downwards. Okay, so you refer to the last page of your notes. If you talk about the charged particle that was moving straight through and deflected, I mentioned to you that your FB would be equals to your FE, where your FB is BQV, your FE is QE. Okay, so if you have a charged particle that is moving with a speed less than V, or speed more than V, your charged particle will deflect downward. Speed less than V, your charged particle will deflect upward. It's based on this. Okay, you see, your BQV gives you your FB. Your FB depends on speed. Okay, so what you can say here is that FB equals to FE is only applicable for this one. Okay, for cases where you have charged particles moving more than or less than that speed V, FB will not be equals to FE. Okay, for this case here, FB will not be equals to FE. Then this one here, FB would not be equals to FE also. One of them will be larger than the other, but how do I know which one is larger than the other? This one here, I can see that speed is less than v is less than this one. So I know speed decrease, my FB must decrease. Therefore, FE is more than FB. Because I know that previously at this point here, when you're moving straight, FB is equals to FE. If I'm moving at a speed less than V, my FB must have dropped because FB depends on speed. So if previously FB is equals to FE, now my FB drop, that would mean that my FE is more than my FB. My electric force is larger than my magnetic force. So based on the charged particle that I have here, where I know FE is upwards and FB is downwards, since FE is larger now, it will deflect upwards. Okay? Now, I can also do the similar analysis for a case where your charged particle is moving with speed more than V. So I know here the speed is larger. That means my FB is larger. So my magnetic force is larger. That would mean that my FB is now more than FE. This is larger than this now. So my charged particle was therefore move downwards. Okay, that's how you see. Right, you have to see the FP FE direction and then see what happens to the FP when you change your speed. That one will allow you to see which force is now larger and in which direction it will move. Okay, so let's just do some of the questions on that. You have 4 velocity selector questions. Go to page 3 of your worksheet. Okay, page 3 of your worksheet. It's actually supposed to be page 2 though. The earlier part of the question is in page 2. Okay. You have November 15 P41. This one is question 6. Okay, so the question asks you right now, you have a particle of mass m, charge positive q and speed v. State the magnitude and direction of force, if any, on the particle when the particle is traveling along the direction of uniform gravitational field of field strength g or uniform magnetic field of flux density b. Okay. Now, if you have a gravitational field, here they say there's uniform gravitational field. By right, the gravitational field should look like this. Okay, this is your direction of your gravitational field. So they tell you that you have a mass that is traveling along the line, so along the direction of uniform gravitational field strength G. So here, you have a mass that is traveling in the direction of the gravitational field. What is the direction of force and what's the magnitude of your force? You know by now that your gravitational force will always be in the direction of your field. The magnitude of that force will be mg. Okay, so the magnitude of your gravitational force is mg. It is always along the direction of the field. If you want to be more specific, you can say it's in the direction of the field. Okay, now for the case where you have a charged particle that is moving along the direction of the uniform magnetic field of flux density B, it will look like this. Okay, uniform magnetic field of flux density B is this 4 parallel lines here. Your charged particle moves along the direction of the magnetic field. It is actually moving parallel to the field. So your magnetic force is 0. Okay, as I mentioned to you, only motion of charged particle charged particle perpendicular to the field will cause magnetic force. If it's parallel, no magnetic force. Okay, so 0 force. That's all there is to it. Okay. Now, if you look at part B, they tell you two charged horizontal metal plates situated in a vacuum produce a uniform electric field of field strength E between the plates. The field strength outside the region between the plates is 0. The particle in A enters the region of the electric field at right angles to the direction of the field. A uniform magnetic field is to be applied in the same region as the electric field so that the particle passes undeviated through the regions between the plate. Okay, they will want the charged particle to move straight right now based on what the question has said. They want your charged particle to move straight. So if your charged particle is to move straight, state and explain the direction of the magnetic field. What must be the direction of the magnetic field here? Okay, so you just consider your positive charge first in the middle of the fields. Your electric field is downwards. That would mean that your electric force is downwards because Fe on positive charge is always in the direction of the field. Okay, so you know your Fe is downwards. If you want to move straight, undeviated, this Fe must be balanced by another force, which is your magnetic force. So your magnetic force must be acting opposite to your electric force in order for you to move straight. So your magnetic force is actually outwards now. Okay, so if your charged particle was moving straight towards the right, this is the direction of your V. Since this is charged particle, since this is positive charged particle moving towards the right, that means the direction of your conventional current is also same direction. So you can use Fleming's left-hand rule right now to determine the direction of the magnetic field. Okay, so stay and explain the direction of magnetic field. You say something like this, no? To pass undeviated, the electric force acting downwards is balanced by magnetic force acting upwards. From Fleming's left-hand rule, the magnetic field is acting into the plane of the paper. If you try to use your Fleming's left-hand rule and orientate your fingers according to FB and I here, you will notice that your B is pointing into the screen, is pointing into the plane of the paper. Okay, so it's acting into the plane of the paper. Okay, so also work with this. Then after that, no issues here, then I will just go to the next part. Okay, so this one is fine now. 2 marks. First mark is using magnetic force acts outwards. Second mark comes from using the magnetic field is acting into the plane of the paper. The rest are just further explanations. Alright, now derive your explanation the relation between speed v and the magnitudes of the field strength E and magnetic flux density B. Now, to pass undeviated, the magnetic force must be equals to electric force. FB equals to FE, BQB equals to EQ, then V equals to E over B. Now, you just wrote this itself, you will only get 1 mark. For some reason, the marking scheme requires you to actually tell us what is your FB, what is your FE. Okay, the rest of the quantities here, the speed V, magnetic flux density B, electric field strength E, and charge Q, the question is really defined for you. But if you want to do the derivation later on to show the relation between V, to show that the relation of V is equals to E over B, you have to use FB equals to FE, right? The other 2 marks actually came from you explaining what is FE, what is FB. Okay, this is the odd thing here for this question. Your 2 marks actually came from you explaining specifically what is the symbol. The only thing I can probably say is because of these wordings here, derive with explanations. So you have to explain the symbols that you use that are not already explained in the question. That won't explain in the question. Okay, that's where you get your other 2 marks from. Alright. Okay, so if this is fine, then I'll go to the next one. Okay, now you have a second charged particle with mass m, charge q, same as that in B, but the speed is 2v. The particle enters the regions between the plates along the same direction as the particle. Now, on figure 6.1, sketch the path of the particle in the region between the plates. Okay. So just now what you had was basically your charged particle Q, right? Positive Q. You can think of it as being this one here. This one was positive Q, right? Positive charge. Your Fe was downwards, your Fb was upwards. So based on what they say right now, you have another charged particle with same mass, same charge, but with a larger speed than before. So what is the path of this new particle in the field? Okay, so here everything else remains the same, only the speed has increased. So your speed has increased to 2v, speed has increased. That would mean that Fb has increased. Now previously, when you're talking about the original charged particle moving with speed v, this one here was Fb equals to Fe. Your second charged particle moves with a speed twice of that of this. Okay, would it deflect outwards or downwards? Would it deflect outwards or downwards? So you have to see from this. If your speed has increased, that means your Fb would have increased. So that would then mean that your Fb is more than Fe. So for the charged particle now, if your Fb is larger, that means you're going to go up. Your new charged particle moving with a higher speed of 2v will actually move up. Okay, so you just draw a charged particle moving upwards. That one will be okay. Alright. So if that one is okay, then you can move to page 5. So this one is V, where Fb is equals to Fe. This one is 2V, where Fb is more than Fe. Okay, if you want to visualize it, what's happening, only the one with V will be Fb equals to Fe. The one with 2V, speed larger than this, Fb is more than Fe. Okay, right, so if that one is okay, you can have a look at page 5 of your worksheet. Page 5 is actually the next page, also somewhat similar. Okay, now March 2016 P42. Okay, question 9. Okay, now you have a particle or charge positive Q mass m traveling with constant speed of 1.6 times 10 power 5 in vacuum. The particle enters a uniform magnetic field of flux density 9.7 times 10 power minus 2 Tesla as shown. The magnetic field direction is perpendicular to the initial velocity of the particle and perpendicular to and out of plane of the paper. A uniform electric field is to be applied in the same region as the magnetic field so that the particle passes undeviated through the field. State and explain the direction of the electric field. So this is a case where you have combined electric and magnetic field so that your charged particle passes undeviated. Okay. They want to find out the direction of the electric field now. The previous question asked you to find out the direction of the magnetic field. This one wants you to find out the direction of the electric field. You would apply the same analysis here. Charged particle positive Q still means it's positive charge. So if you use Fleming's left-hand rule, where is FBI, they already told you your magnetic field is out of the plane of the paper. This is positive charge moving undeviated. So this is your V. This is also your conventional current. So again, if you use Fleming's left-hand rule on this situation now, where you go and orientate your fingers according to direction of B and I, you will notice that your FB is upwards. For your charged particle to pass undeviated, you must balance this force. So your electric force must be downwards. Okay. So as I mentioned to you, Fe on positive charge follows direction of E field, right? So your electric field direction must be downwards. So your explanation will be something like this. The force due to electric field will act in the opposite direction to force due to the magnetic field. The electric force is acting outwards on a positive charge, hence the direction of the electric field is upwards. It's upwards. Did I do my question wrongly? Oh, sorry. My FP is wrong. Okay. Because this one is out of the plane of the paper, meaning to say your index finger must be pointing towards you. Okay. So if you orientate your Fleming's left-hand rule according to the direction of B and I, your magnetic force is actually pointing downwards. Sorry, my mistake. Your magnetic force is downwards. Okay. So your electric force must be acting outwards to balance this so that you pass undeviated. So since your electric force on positive charge is outwards, your direction of electric field is in that same direction. Okay. The line of reasoning is still the same now. It's just that I made a mistake in the direction just now for FB. Okay. Force due to electric field acts in opposite direction to force due to magnetic field. The electric force is acting outwards on a positive charge, hence the direction of the electric field must be upwards. Okay. Right. Then calculate the magnitude of the electric field strength. For the charged particle that is moving in the undeviated, magnetic force must be equals to electric force. So this one will be FB equals to, magnetic force must be equals to electric force. It will be BQB equals to EQ. Okay. Even if you don't explain this one, what is FE, what is magnetic force, this one is fine actually. It's only the previous question just now that you needed to explain. You needed to explain because of this weird statement here. But for this case here, you can actually just get away with just saying FE equals to FB. No issues here. Okay. So eventually you find out that E is actually BV. B is given to you 9.7 times 10 power minus 2 Tesla. V is also given to you, it is 1.6 times 10 power 5. Okay, so you get your answer is 1.55 times 10 power 4. Okay, right? So that one is fine. Okay, then if you go to the next part of your question, the electric field is now removed so that the positively charged particle follows a curved path in the magnetic field. The path is the arc of a circle of radius 4 centimeter. Calculate for the particle the ratio of Q to M. Now here they tell you remove off your electric field. Okay. Previously in your current case, the previous case, you have both electric and magnetic field. So you have both magnetic and electric force. Those two in turn cause your charged particle to move in a straight line, where that time FB is equals to FE. Now the question tells you remove your electric field so that your positively charged particle follows a curved path in the magnetic field. Now when you remove your charged particle, when you remove your electric field, that means you no longer have an electric force. You only have your magnetic force now inside the magnetic field. So your charged particle will actually start to move in a circle. In this case here, FB is FC. Okay, so they want the ratio of Q to M. FB is FC, FB is BQB, FC is mv squared over R. So they want the ratio of charge to mass. You just rearrange it in such a way that it's Q over M. Then you get V over BR. V you know, B you know, the radius of the circular path you also know. So you just sub it in, you get the ratio as 4.12 times 10 power 7. Okay, so no issues there. Okay, so if this one is okay, then you move on to the next one. They told you that the particle has a charge of 3e, where E is the elementary charge. Use your answer in C to determine the mass in U of the particle. Okay, you already have the value of charge per unit mass, which is 4.12 times 10 power 7. This is your answer in C. They want you to determine the mass U of your particle. Okay, so if they already give you the charge of the particle as 3e, you know this, you can find out what is M. Okay, so you just sub in your values to find out the value of M. It will be 3e divided by 4.12 times 10 power 7. You get the answer in terms of kg. You want to find it in terms of U, so you divide by the unified atomic mass, 1.66 times 10 power minus 27, which is from your data sheet. You eventually get your answer as actually 7U. Okay. Alright. Okay, so you get the answer as 7U. Now they tell you that the particle is the nucleus of an atom. State the number of protons and the number of neutrons in this nucleus. Okay, so that particle, charged particle that you have is actually a nucleus. And nucleus, you know, has only protons and neutrons, right? So when you talk about 1U, this one was mentioned to you before. It's kind of like the average mass of a nucleon. So if your mass of the nucleus right now is 7U, that means you have 7 nucleons. All right, which consists of protons and neutrons. So how do you determine how much is the number of protons, how much is the number of neutrons? Okay, the charge of your nucleus comes from your proton. Okay, your proton has charge, right? But your neutron has no charge. Okay, so you know that there are 7 nucleons, but you also know that the charge of your nucleus is 3e. That means you have 3 protons here. So therefore, the remaining number 4 must be your neutrons. Okay, that's how you understand it. Okay, so you have this one done. Then after that, you can go to look at page 21. Okay, so have a look at page 21. Okay. Okay, page 21, statewide member, page 21, this one is November 17 P42. Okay. Right, what is meant by a field of force? They're not asking you for magnetic field, electric field, gravitational field. They're just asking you for a field of force. A field of force in general is just a region where a particle experiences a force. Okay, so that's all there is to it. All right. Then after that, there are some cases where your questions will require you to describe how do you use electric and magnetic field to select velocity of certain charged particles. It's actually related to what I explained to you in the notes just now here. You have to use a combined electric and magnetic field to select charged particles of a certain velocity. The velocity of the charge, the particle with the velocity you select will move in a straight line. So what you need to do is you just need to draw this diagram and just write these things. Okay. You say that you set up electromagnetic field perpendicular to each other. The velocity of charged particle is normal to the field. The force on the particle due to fields are in opposite direction. The forces are equal for particles with a selected speed, given by V equals to EV. Okay. So if anything, probably you might need to add this statement here also if you want to be more specific. Magnetic field into plane of paper, and then after that electric field acting downwards. Okay, so this one should be okay. So if you have a charged particle inside like this, where your V is this side, your magnetic force is downwards. Sorry, not magnetic force downward. I made the mistake again. Your magnetic force is upwards. Okay. Whereas your electric force is downwards. Okay. So just take a minute or two to copy this. The last one I can do for you is page 27. I would suggest you draw the diagram now, okay? There's a reason why if you don't draw the diagram, you just read this, it's very hard to understand, isn't it? So I would suggest you draw the diagram, okay? You may draw a diagram if you wish. Yes, you may draw a diagram if you wish. But are you that confident that you don't draw a diagram, you just explain like this, the examiner will be able to understand what you're saying? It's a risk lah. You can choose not to draw if you wanted to, but please make sure that what you describe is very clear to the examiner. Okay? Else, I would always suggest try to draw something and then you write, at the very least people would know what it is. Okay? Yep, just in case. It's better to have a diagram for the examiner to be able to refer to as compared to you write something, people don't know what you're talking about. Okay, right? So that part is fine. Then we go to page 27. Okay, this one should be the last one. Okay, so if this one is okay, then you can have a look at page 27. 27 is actually, page 27 is actually the same thing again. Okay, June 18 P42. The first part is actually the same question again. But you see this one here is now worth 3 marks. The one that you see just now in page 21, November 17 P42, is actually talking about the same question, but this one they give you 4 marks. This one in page 27, June 18 P42, same question again, but they give you 3 marks. It's basically the same answer lah. Okay, what you just need to do is that if you take this one and you put it inside here, you will get the full marks. Okay, so this one you can just do it later lah. You can just recopy back what you just did in the previous question. Okay, now I want to go through part B. Now part B, they tell you particles having mass m and charge 1.6 and 10 power minus 19 coulomb pass through a velocity selector. They then enter a region of uniform magnetic field of flux density 94 millitesla with a speed of 3.4 times 10 power 4, as shown in figure 8.1. Then they ask you the direction, they tell you the direction of the uniform magnetic field is into the page and normal to the direction with which the particles are moving. The particles are moving in a vacuum within a circular arc of diameter 15 centimeter. Show that the mass of one of the particles is 20 U. Okay. The velocity selector that they're talking about is this part here. This part here is where you have E field and B field perpendicular to each other. This was the part where your FB equals to FE. Now, whatever particle of a certain speed you select will come out here, and then it will go into this region here. Okay, this region here has B field only. So your charged particle that comes into this region of B field only, FB is FC. So the equation you apply is also different. Huh? That's why here you see this one moves in a circle in the first place. They ask you to show that the mass of one of the particles is 20 U. You try to refer to it based on this section here. You try to solve based on this section here because the information that's given is for this section. So you say the magnetic force provides centripetal force. FB equals to FC, BQV equals to MB squared over R. Then you sub in the values to find M. You know the B, you know the Q, you know the radius. Radius is not given directly, they give you the diameter. You have to divide by 2 to get the radius. And then the velocity, they've also given to you 3.4 times 10 power 4. Sub that in, get the mass in kg, and then divide by uniform atomic mass U to get the value in U. Okay, so that part is okay. Okay, so this one is okay, then you can move on to the very last part here. Okay, so now they tell you on figure 8.1, sketch the path in the uniform magnetic field of particle mass 22U having same charge and speed as particle in B. Okay, how will be the path of the particle having this mass but this same charge and speed? Okay, so as mentioned to you, anything that goes into any charged particle that goes into a magnetic field only, FB is equals to FC, right? So eventually you got this equation, right? BQV is equals to MV. Eventually you get to this expression, M is BQR over V. So for your second case here, you know a few things. Previously your mass is 20U, now your mass is 22U. It means your mass has increased. They say you have the same charge and speed, that means Q and V constant. Okay, so from there, if you apply to this equation, M is equals to BQR over V, you will actually be able to say that M is proportional to R. If your mass increase, your R increase. Okay, now your B is also the same because they say sketch the path in the uniform magnetic field. So this one, your B is also constant because you're causing the charged particle to move inside the same field. Your B is constant also. So B constant, Q constant, B constant, M is proportional to R. Bigger M, bigger R. So sketch the path. Just draw your charged particle moving in a semicircle again, but with bigger radius. Bigger radius means bigger diameter. Okay, so just draw that part and you should be fine. So for this one, I think you need to use a compass. It is very hard to draw freehand. Okay, so for your actual exam, I would suggest you use a compass.